Hello dear viewers, welcome to TV Mathshub. In our previous session, we talked about linear combination of vectors. And in this session, we are going to look at linearly independent and linearly dependent vectors. So by the end of this session, I expect you to be in position to explain what it means for vectors to be linearly independent or dependent. You should be in position to test whether a given set of vectors is independent or dependent. If you find this video helpful, please don't forget to subscribe, like and share this video with your friends. It really supports the channel. So without wasting time, let us get started. So we shall be talking about linearly dependent and linearly independent sets. So when you are given a non-empty subset of a vector space V, which is S. So if you have S, and this S here is a non-empty subset of V. In other words, it is consisting of the vectors V1, V2 up to Vn. Then we shall be saying that this set here, which is consisting of these vectors, is linearly dependent if we are able to get some scalars alpha 1, alpha 2 up to alpha n, which all these scalars here are not all equal to 0, such that when you get alpha 1 times V1 plus alpha 2 times V2 plus up to alpha n Vn, you get 0. So in other words, we are saying if you are having your system of vectors, you are having your vectors V1, V2 and V3, for example, and you have the scalars alpha 1, alpha 2 and alpha 3. So if you get alpha 1 V1 plus alpha 2 V2 plus alpha 3 V3 and you equate this one to 0, then you solve this equation here for the values of alpha 1, alpha 2 and alpha 3. But you get the values, for example, alpha 1 is not equal to 0. You get alpha 2, maybe it is equal to 0. And alpha 3 maybe is not equal to 0. So you realize that some of the scalars, alpha 1 and alpha 3 are not equal to 0. Then we shall be saying that these vectors here, V1, V2 and V3 are linearly dependent. So it means for these vectors to be linearly dependent, the values for the scalars alpha 1, alpha 2 and alpha 3 should not be, all of them should not be equal to 0. One of them must not be equal to 0. But when you realize that the values for alpha 1, alpha 2 and alpha 3, when you equate this linear combination to 0, you realize that the values for alpha 1, alpha 2 and alpha 3, all of them are equal to 0. Alpha 1 is equal to alpha 2, which is equal to alpha 3, and all of them are equal to 0. Then we shall say that these vectors V1, V2 and V3 are linearly independent, meaning that the linear independence occurs only when all the scalars are equal to 0, meaning that the only value for these scalars is 0. But when one of the scalars is not equal to 0, then we shall be saying that the vectors considered are what we call linearly dependent. We shall also put this note here that two vectors are linearly dependent if and only if one is a multiple of the other. For example, if you have u as 2 and negative 3, you have v as 6 and negative 9. So you realize v can be written in terms of u. In other words, v is same as 3u. V is same as 3u. In other words, when you have 6 and negative 9, this is same as 3 into 2 and negative 3. Okay, so when you are to check whether the scalars are all equal to 0, surely the scalars would not be equal to 0. For example, when you say alpha 1 into 2 and negative 3 plus alpha 2 into 6 and negative 9, which is equal to 0, 0, then you will realize that alpha 1 and alpha 2 will have values other than zeros when you solve this equation. Now, that is what it means, meaning that if one vector can be expressed in terms of the other, then they automatically become linearly dependent. They automatically become linearly dependent. So let us look at the examples to understand more about this concept for linearly independent and linearly dependent sets. So we shall look at examples to understand that. So in our first example, we are given the set S, which is consisting of these vectors. Then we need to determine whether the set S is linearly dependent or not. So for that case, we shall try to write the linear combination of these vectors here, then we equate it to 0. Then after equating it to 0, we get different equations which we shall solve for the different values of the scalars. And from the values of the scalars, we shall be in position to tell whether S is dependent or independent. So how do we do that? So let us look at the solution. So looking at the solution, we are given the set S, which is given by the vectors 1, 2, 1, 2, 1, 4, then 3, 3, and 5. So this is our set, and we need to find out whether this set here is linearly independent or linearly dependent. So what we shall do here is, one, what we need is we need to show that there exists, we need to show that there exists scalars alpha 1, alpha 2, and alpha 3 such that when you get alpha 1 v1 plus alpha 2 v2 plus alpha 3 v3, this should be able to give you 0. Meaning the linear combination, when you are testing for linearly independent and linearly dependent, you equate the linear combination to 0. Okay, so from here, let us substitute for v1, v2, and v3. So we are letting our v1 to be this, our v2 to be this, and our v3 to be this. So from here, we shall therefore say alpha 1 into v1. v1 is 1, 2, 1. Then plus alpha 2 into v2. v2 is 2, 1, and 4. Then next is alpha 3 into v3 is 3, 3, and 5. You must equate this to 0, and the 0 in a 3 dimension will be 0, 0, and 0. Okay, so from here you need to get the corresponding elements. We have this as alpha 1, 2 alpha 1, and then alpha 1. We are multiplying this alpha 1 here. Then let us also multiply alpha 2 inside for alpha 2. Then also let us multiply this alpha 3. And this should be equal to 0, 0, 0. So from here, we can equate the corresponding components. So alpha 1 plus 2 alpha 2, then plus 3 alpha 3. Then we shall have 2 alpha 1 plus alpha 2 plus 3 alpha 3. And lastly, we shall have alpha 1 plus 4 alpha 2, then plus 5 alpha 3. And this should be equal to 0, 0, 0. So from here we shall equate the corresponding components. So the corresponding components are alpha 1 plus 2 alpha 2 plus 3 alpha 3, which is equal to 0. We shall have 2 alpha 1 plus alpha 2 plus 3 alpha 3, which is equal to 0. We shall have alpha 1 plus 4 alpha 2 plus 5 alpha 3, which is equal to 0. So that is basically what we are having. So this, we can call it equation 1. We can call this equation 2. We can call this equation number 3. So from these 3 equations, we shall solve for the values of alpha 1, alpha 2, and alpha 3. So let us see how best we can solve these equations simultaneously. So next we shall say solving the equations simultaneously. Solving equations 1, 2, and 3 simultaneously. We shall have, let us begin by considering equation number 1 and equation number 2. So equation 1 says we have alpha 1 plus 2 alpha 2 plus 3 alpha 3, which is equal to 0. We have 2 alpha 1 plus alpha 2 plus 3 alpha 3, which is equal to 0. So we need to eliminate one unknown from here. So we can eliminate alpha 1 by making this one 2 also. Then after we shall subtract. So this will give us 2 alpha 1 minus 2 alpha 1, which will be 0. 2 times 2, that will be 4, minus 1, that is 3. So that is 4 alpha 2 minus alpha 2, which is 3 alpha 2. Then this will give us 6 alpha 3 minus 3 alpha 3, which will give us plus 3 alpha 3, and this will give us 0. So divide it through by 3, and this will be alpha 2 plus alpha 3, which is equal to 0, and this will become equation number 4. So next we shall consider, let us consider equation 1 and equation number 3. So what is equation 1 and what is equation number 3? So this is equation 1, this is equation 3. So we shall have equation 1 is alpha 1 plus 2 alpha 2 plus 3 alpha 3, which is equal to 0. Equation 3 is alpha 1 plus 4 alpha 2, then plus 5 alpha 3, which is equal to 0. So we need to also eliminate alpha 1, and since the coefficients are the same, we shall now subtract. This will be minus 2 alpha 2, 3 alpha 3 minus 5 will also give us minus 2 alpha 3, and this will be equal to 0. So from here, simply so let us simply divide through by negative 2, and this will give us alpha 2 plus alpha 3, which is also equal to 0, and this will be equation number 5. So from the equations, let us say from equations 4 and 5, from equations 4 and 5, we shall have alpha 2 plus alpha 3, which is equal to 0. Then alpha 2 plus alpha 3, which is equal to 0. This is equation 4, this is equation 5. So from here you realize alpha 2 we have alpha 3, alpha 2 we have alpha 3. So they are the same equations. So in other words, if you subtract, all these ones will give you that is 0, 0, which is equal to 0. And if you get 0 is equal to 0, this is true. However, this one implies that this system has got infinitely many solutions. This system has infinitely many solutions. So what do we do then? So to get the solutions, what we shall do is, we shall, since these equations are the same, we shall simply possibly let, for example, alpha 3 to be like t, where t is any real number, where t is any real number. So when you get 0 is equal to 0, 1 is equal to 1, that one is true, but that simplifies, so this will simplify that our system has got infinitely many solutions. So you let one scalar to be in terms of some other parameter. For example, alpha 3 is in terms of t, where t is any real number. So from there, get the values for alpha 1, alpha 2, and alpha 3 in terms of t. So we can now say from maybe 5, alpha 2 plus t will be equal to 0, meaning that this implies that alpha 2 is same as negative t. So we have got alpha 2, we have alpha 3, so we need alpha 1. So again, we shall now look for alpha 1. We can use any of the equations that we have. So possibly let us choose one of the equations here. We can take maybe equation number 1. So let us have from equation 1, from equation 1, which equation 1 is saying alpha 1 plus 2 alpha 2 plus 3 alpha 3 is equal to 0. This implies that alpha 1 plus 2 alpha 2. Alpha 2 we have seen, alpha 2 is negative t. So this is negative t plus 3t, which is equal to 0. So alpha 1 minus 2t plus 3t is equal to 0. And alpha 1 will give us, this will be t, this will be negative t. So that will be alpha 1. So from here we have got the values for alpha 1, alpha 2, and alpha 3. So let us go on and say, therefore, we shall have alpha 1 here, alpha 2, and alpha 3. So what will be the values for this? Alpha 1 is negative t. Alpha 2 is also negative t, and alpha 3 is also t. So that is what we shall have, and this is same as having negative 1, and 1 into t. So we are saying that t is any real number. So it means for any value of t, we shall be able to get alpha 1, alpha 2, and alpha 3. So having got the values for alpha 1, alpha 2, and alpha 3 in terms of t, where t is any real number, so we can now conclude that thus for any parameter, t, which is picked from a set of real numbers, the system has a non-zero solution. Thus, S is linearly dependent. For it to be linearly independent, the only solution should be a zero solution, meaning that alpha 1 should be equal to 0, alpha 2 should be equal to 0, and alpha 3 should be equal to 0. But if alpha 1, alpha 2, and alpha 3 have got any other solution other than the zero solution, then we say that the system is linearly dependent. I hope this one is okay. Because for any value of t, if you put t as 0, alpha 1 will be 0, alpha 2 will be 0, and alpha 3 will be 0. But t can also be 1. If t becomes 1, alpha 1 will be negative 1, alpha 2 will be negative 2, will be negative 1, alpha 3 will also be a positive 1. So you realize that this is not the only solution. For any value of t, we can get this as a solution, we can get this as a solution, we can get as many solutions as possible for any value of t picked from the set of real numbers. But if we had only this, if we had this one as the only solution for the values of alpha 1, alpha 2, and alpha 3, then we would say that our set is. So that is our example number 1, and we shall look at one more example to understand better about this concept for linearly independent and linearly dependent vectors. So let us look at example number 2. So the example number 2 says, let V be a vector space of a 2 by 2 matrices over R. Determine whether the matrices A, B, C, which are picked from the vector space V, are linearly dependent or linearly independent. Where we are given our A as that, our B as that, and our C as that. So that is basically what we need to look at in our example number 2. So let us look at the solution. So we are looking at example number 2. So in example number 2, we are given a vector space V, which is a 2 by 2 matrix, and has got matrices A, where A is 1, 1, 1, 1, B is 1, 0, 0, 1, C is 1, 1, 0, 0. Now we need to determine whether these matrices A, B, and C are linearly dependent or linearly independent. So we look at the solution. So to do that, we shall basically set the linear combination. We shall basically set the linear combination of the matrices A, B, and C to be equal to a zero matrix. And we shall do that using the unknowns or the scalars. We can use alpha 1, alpha 2, or alpha 3, or we can use x, y, and z. So these are our scalars. So that will imply that we shall set the combination, linear combination of the scalars and these matrices. That will be xa plus yb plus zc to be equal to 0. That is what we need. And from here, you need to get your scalars x, y, and z. And if the scalars are all equal to 0, then you will say a, b, and c are linearly independent. If the scalars are not all equal to 0, then you say they are linearly dependent. So from here, let us go on and substitute for a, b, and c. So this is x into a, 1, 1, 1, 1, plus b. B is that, so we have y into b, 1, 0, 0, 1. We have z into c, 1, 1, 0, 0, and this should be equal to a 2 by 2 0 matrix. So from here, we can multiply x and have x, 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 and x. This will be y, 0, 0, y. This will be z, z, 0, and 0. And this should be equal to 0, 0, 0, and 0. So from here, let us add the corresponding components. This is same as x plus y plus z. This is x plus 0 plus z, that is x plus z. I'm adding this with this together with that. Next, x with a 0, again with a 0, so that is x. Next, x with y, again with 0, that is x and y. And this should be equal to 0, 0, 0, and 0. So that is basically what we are having. So from this given point, when we have these two matrices equal, then we must make sure all these corresponding components are also equal. So for that case, let us equate the corresponding entries on each of the sides. So this will be, this will give us, we are equating the corresponding entries. So equating the corresponding entries, we shall have you equate x plus y plus z to 0, this to 0, x to 0, this to 0 as well. So we shall have x plus y plus z, x plus y plus z equaling to 0. We shall have x equaling to 0. We shall have x plus z equaling to 0. We shall have x plus y equaling to 0. So we shall obtain 4 equations. And from these equations, we need to get the values for x, y, and z. So we have already got the value of x. Let us substitute and get the value of y. We substitute and get the value of z. So from 3, which is saying x plus z is equal to 0. So 0 plus z is equal to 0, and z is equal to 0. From 4, x plus y is equal to 0, but we have x as 0, so 0 plus y is equal to 0, and y is equal to 0. So it is clear. That x is equal to 0, y is equal to 0, and z is also equal to 0. So if you get the scalars x equaling to 0, y equaling to 0, and z equaling to 0, what does that one mean? So it means that the matrices, since the only solution to the scalars to the scalars x, y, and z is a zero solution, is a zero solution, is a zero solution, it implies that the matrices, A, B, and C are linearly independent. So if you find that the only solution to your scalars is a zero solution, then it means the vectors or the matrices that you will be considering will be linearly independent. But if you find that the zero solution is not the only solution, there are also other solutions, then you will conclude that they are linearly dependent. The same applies if, for example, z was not equal to 0, but y is equal to 0 and maybe x is equal to 0. If one of the scalars is not equal to 0, still you cannot conclude that they are linearly independent. It means they are linearly dependent. So long as one of the scalars is not equal to 0, then you conclude that your vectors are linearly dependent. So that is our example number 2. And from example number 2, we can look at one more example. And from there, you'll be able to try some few other numbers. So we have example number 3, where they are saying determine whether the vectors this and that are linearly independent or linearly dependent. You will try this out. You will try this one out using the same procedures that we did in our first example. So I want to try one example here where they are saying that show that this is linearly independent. So that is what basically we need to try together. And then you will be able to try this one out. You try this one out as well. So let us look at this example here. They are saying show that the set, this one here, is linearly independent. So we shall use the same procedures as we did in our first example. So we are given the set S. This will be example number 3. We are given the set S, which set is consisting of vectors 1, 1, negative 1. The set is consisting of 1, 1, 1, then 1, 1, 0, then 1, 0, 1. So that is what we are having. This is our set S. So like the way we did in our example number 1, we shall seek for the scalars such that the linear combination is equated to 0. So we shall relate this one to be V1, this one to be V2, and this one to be V3. So we shall be saying that we need to show that there exists. We need to show that there exists. We need to show that there exists scalars. Can have alpha 1, alpha 2, and alpha 3, such that the linear combination, that is alpha 1 V1 plus alpha 2 V2 plus alpha 3 V3, is equal to 0. So let us have our alpha 1 into V1. V1 is 1, 1, 1, plus alpha 2 into 1, 1, 0, plus alpha 3 into 1, 0, 1. And this should be equal to 0, 0, 0. A 0 vector in R3 will be having 3 components consisting of zeros as well. So from here, I will do this at once. This is alpha 1. I will be adding there alpha 2. I will be adding there alpha 3. This will be alpha 1. This will be alpha 2. And this is 0. So we shall have that. Next, we shall have alpha 1. This is 0. and this will be alpha 3. So that is basically what we shall have, and this is equal to 0, 0, 0. So from here we shall obtain equations, that is alpha 1 plus alpha 2 plus alpha 3 is equal to 0. We shall have alpha 1 plus alpha 2 is equal to 0. We shall have alpha 1 plus alpha 3 is equal to 0. We can call this equation 1, equation 2, and this equation number 3. So we shall solve these equations simultaneously and get the values for alpha 1, alpha 2, and alpha 3. So basically, let us consider equation 1. Consider equation 1 and equation number 2. So from equation 1 and equation number 2, you realize equation 1 and equation 2, you realize we have alpha 1, this is alpha 2 and alpha 1 in equation 2, but here we have alpha 1, alpha 2, and alpha 3. But this equation we have alpha 1 and alpha 3. So I will consider these two equations and I eliminate alpha 2, so I can remain with alpha 1 and alpha 3. So I will consider alpha 1 plus alpha 2 plus alpha 3, which is equal to 0. Then alpha 1 plus alpha 2, this is also 0. So I will eliminate alpha 2. So to eliminate alpha 2, you actually also eliminate alpha 1. So this is 0. This is also 0. So you remain with alpha 3, which is equal to 0. That is what we shall remain with. So clearly, we have alpha 3, which is equal to 0. So our alpha 3 is equal to 0. So we need to get alpha 1 and alpha 2. So from equation, from this equation 3, from equation 3, we shall have, equation 3 is saying that alpha 1 plus alpha 3 is equal to 0. Alpha 1 plus alpha 3 is equal to 0. Okay, so alpha 1 plus alpha 3 is equal to 0. That is equation number 3. So alpha 3 is 0, we have got that, but alpha 3 is equal to 0. So this implies that alpha 1 plus 0 is equal to 0, and alpha 1 is equal to 0. Next, let us look at from equation 2. From equation 2, I think we can get alpha 2, yes. From equation 2, it is saying alpha 1 plus alpha 2 is equal to 0, but alpha 1 is 0, so it means 0 plus alpha 2 is equal to 0. So alpha 2 is also equal to 0. So what do we have? This implies that alpha 1 is equal to 0, alpha 2 is equal to 0, and alpha 3 is equal to 0. So the only solution to this system here is a 0 solution. So if the only solution to our system is a 0 solution, then you should know now what the vectors v1, v2, and v3 are. So for this case, it means our vectors v1, v2, and v3, or the set S, is actually linearly independent. And from there we shall have shown, because our question was to show that this set here is linearly independent. So we shall clearly be in position to give a conclusion that the set S is linearly independent, since the only solution to our system that we have got is actually a 0 solution. So let us write and say since the only solution So that will be our conclusion, that since the only solution to the system of equations is a zero solution, then clearly S is linearly independent. And from there you will have shown that S is a linearly independent set. But in case one of the unknowns is not equal to 0, then that one becomes linearly dependent. So from these examples that we have seen so far, you should be able now to try some of these questions here. You try this one, try this one, and try this one here. And please don't forget to subscribe to this channel. Simply hit the subscribe button, like and share this video to your friends. So that's all for today, and we meet in our next session.
Yeah.